So it's been a year since we hosted one of these. We've got some really exciting results to show. We're a new team. We've been working really hard. And we're going to talk today a bit about progress towards our mission of radically extending human health span. In a minute, I'm going to invite up some other co-founders, members of the team, and at the end, we'll have time for Q&A. Okay, so our mission is to radically extend human health span. The company was founded really on this observation that all of the major diseases which take us out in life, whether it's cancer, heart disease, diabetes, dementia, they're all correlated with age. And our medical system today is really focused on treating each of these diseases individually, but what if there was some kind of common cause underneath all of these, which is that as we age, our cells lose function, they lose resiliency, they lose the ability to recover from damage or insults to these cells. And if we were able to actually restore the function that our cells had when we were younger, maybe we would be able to attack the root cause of a lot of these diseases. So NewLimit is focused on this area of research called epigenetic reprogramming or partial reprogramming. And this is a way to restore function in cells, and maybe we can actually tackle this problem. Now, this is not some completely pie-in-the-sky idea. Prior research has shown that you can take a cell from an aged mouse, do a form of reprogramming on it, somatic cell nuclear transfer, clone that animal. People previously, they thought, well, the clones would have shorter lifespans because you're cloning it from an aged cell that had accumulated this supposedly irreversible damage. But we now know that this was a surprising result. This was false. Actually, the clones lived a full and normal, healthy life, and you could do this over successive generations, and each generation actually lived a full, normal, healthy life. So this is not just true in mice. We know that it's true in humans as well. Shinya Yamanaka won the Nobel Prize in 2012, showing you could take an old skin cell and reprogram it, changing both the cell age and the cell type with just 4 transcription factors. Now, transcription factors are really just genes that turn on and off other genes, and there's thousands of them in human cells, but it turns out if you expose the cell to just these specific 4, it actually reprograms the age and the type of the cell. Subsequent research showed that you can actually move just on the y-axis, changing just the type of the cell with other sets of transcription factors. For instance, turning a skin cell into a liver cell, a neuron, or a vascular cell. And so it turned out that our cells are actually far more plastic than we originally thought. And so if we can move on the y-axis, can we move on the x-axis? And this is really what NewLimit is attempting to accomplish. We're trying to see if we can change cell age without changing the cell type. And to do this, we're going to have to discover novel sets of transcription factors. Now, this is a hard problem for a number of reasons, but one reason is that the search space of transcription factor combinations is massive. There's thousands of them in human cells. Let's say we narrowed that down to just 400. How many combinations of 5 are there out of 400? Turns out to be a big number, 10 to the 10. That's more than all the single cell sequencing done on planet Earth to date. And so if we're going to crack the password here to this solution, we can't just do a brute force exhaustive approach. We're going to have to build a system or a machine that does this in a more intelligent way. And that's exactly what we've done. Last year, we showed you this diagram of what we call NewLimit's discovery engine. It's a funnel. It starts at the top with this software machine learning layer. We've ingested now and built this proprietary data set from our initial pooled screens. And every time we create new data, we feed it back into the machine learning model. It recommends the next sets of pooled screens that we want to do, still at a pretty large scale. And when we get our pooled screens done, we take the phenotypic hits coming out of that, and we run it through functional assays and preclinical models, eventually human trials. So this is what we spent the last year building, and we just started to ramp up really in the last quarter or 2. So we've got some exciting results to show you today. Hopefully you're all excited to see it. How's it going? Yeah. All right, the engine is working. I am proud to report the engine is revving up. So previously, the field had tested about 20 different partial reprogramming sets. Right now, as of today, NewLimit has tested almost 4,000, about 200x the cumulative amount done in the field that we're aware of in existing literature. And this is a progress update, so we're going to be seeing some metrics throughout the presentation here, giving us a little bit of a year-over-year accountability score. So last year when we were up here, we had tested about 140 reprogramming sets. Today we're at almost 4,000. That's 26x year over year. And it's not just about scale. We're actually starting to get phenotypic hits. So I'm proud to report that we've actually gotten our first 23 phenotypic hits out of the discovery engine. These are now ready to go on for functional validation, which you're going to hear more about a little bit later today. And as we've been driving up the scale, we've also been relentlessly driving down the cost, because that allows us to get more shots on goal. And through dozens of iterations, we've actually had a 75% reduction in the cost per set tested. I think we have line of sight to reduce this substantially more in the coming years ahead, by the way. And lastly, I never want to measure number of employees as always up and to the right is good, because we pride ourselves in being a very scrappy company. But we have done over 100 screens or so for every offer that went out, and we added an additional 15 amazing teammates. It's really ultimately the employees at the end of the day that allowed all this research to be possible. By the way, we also raised our Series A. I want to give a big shout out to Dimension Capital, Kleiner Perkins, and Founders Fund for investing in this ambitious and important mission alongside us. So thank you very much for that. All right, so before I turn it over to our next speaker, I just want to touch on for a moment why I think this research is so important for humanity and why it's something that I hope more people work on. So most people, when they think about extending their lifespan, they imagine themselves in this aged state, a disabled state, and prolonging that experience, which doesn't sound very pleasant. And we agree with that. That's not what we're trying to do here at NewLimit. What we're really trying to do is extend this center bar, the healthy years of our lives. And each of us, we really only get a precious few decades to really do our best work. Some of us, we manage to not have any issues till later in life. Some of us, it's unexpected and it happens sooner. But we never know when that might come. The only thing that's certain is that all of us are eventually going to succumb to one of those diseases today, and we'll slowly have less energy, less cognitive ability. Most Nobel laureates, they did their breakthrough work in their 30s and their 40s. And so I think it's actually a real shame that after we become formative through our formative years, we only get this brief moment to really try to give back to society. And right around the time we start to collect our wisdom and experience, our bodies and our minds start to give out. So I think you could make an argument that aging is actually the greatest source of human suffering on the planet. We've all had friends and family who have succumbed to one of these diseases, or they reach old age and they can't even remember the loved ones that they helped raise, which is a tragedy. And just very tactically, there's 56 million people who die every year. In any other context, that would be considered the largest humanitarian tragedy on the planet. But because it's been normalized, because it's happening from aging, we don't think of it that way. We think of it as something irreversible. We put it out of our mind. In my view, this is the decade where we have a chance, with the state of technology, with machine learning, single-cell sequencing costs declining, that we could actually make a dent in this problem and really show progress on it. But it's going to take smart people coming together and working really hard to make it happen. And so I hope more people join us on this mission and work on aging research.
Thanks so much for all of you for coming and joining us today. And thanks to Brian for really introducing the why behind our mission here at NewLimit. I want to transition now, and for really most of the rest of this talk, to talk about the how. How might we take these medicines we imagine that extend our healthy years and bring them from our imagination to reality? As Brian noted, we have a year-over-year theme we're going to present to you today. We have a lot of metrics we're really proud of. So many so that we've thrown them all on a slide that's probably hard to digest at once. So we're going to break this up into a few pieces, and each of us is going to focus on just one section. So for the next few minutes, I'm really going to focus on that discovery engine that Brian discussed, how we've managed to scale that up about 20-fold. So we've tested many more transcription factor sets for their effect on cell age and started to find really our first hits. If you'll let me be cheeky about it, we've infinitely increased the number of novel TFs we know that are able to change cell age. So before I jump in and show you some exciting data from those experiments, it's useful to just ground ourselves in what those experiments are. So I'll try and run through this quickly. We start out with primary human cells. These are cells from real people. They have a normal number of chromosomes. They're from young and old people. These are not cell lines that are difficult to interpret. They really reflect human biology. That makes our lives harder, but the data more relevant for human disease. And we introduce a number of transcription factors all at once. Based on the randomness of life, each cell gets a different set of those. So you can take a pool of transcription factors we're excited about, and each one of those cells is going to get a different set. We can then turn them on and turn them back off, mimicking what would happen if we gave these to you as a medicine. And we can profile these cells with single-cell genomics. We measure every gene they're expressing all at the same time. And we can take all of that really complicated data and ask a pretty simple question, which is, are there any sets of these TFs that when we put them in an old cell, cause it to express genes that make it look like a younger version of itself? And we hope that by making an old cell look like a younger version of itself, maybe it'll act like a younger version of itself too, function better, and eventually help a patient. And so we introduced the idea of those experiments about a year ago. But admittedly, we hadn't actually done that many of them. It was more cartoon than it was data at that point. And as Brian alluded to, it took us about a full year to overcome a number of technical roadblocks that were necessary to start running those experiments at scale, so that most of the data we've collected today, and the vast majority of the data that exists in the world to our knowledge on what happens when you do partial reprogramming with different transcription factors, was gathered here in about the last 3 months, just right upstairs. So we tested thousands of these reprogramming factor sets. And each one of those points isn't just a unit on a y-axis there on that bar graph, but it's actually a really rich piece of information. It tells us what happens when you turn those TFs on in an old primary T cell. What phenotypes does that cell then adopt as a result? So each of those points in that spinning visualization you see to your right represents one of those transcription factor sets. And you'll see they start to cluster in these little balls. We've indicated them with some colors. Each of those is really a unique phenotype you can make these cells adopt. And we're hoping that we find some examples of transcription factor sets, and maybe some clusters of them, that take an old cell and push it in the direction of a young one, and that cell might then function more like a young version of itself too. And so I want to try and take you all on the emotional journey of what that's like as we've been watching these data come off of our instrumentation over the past year or so. Just 8 months ago, we had hardly explored any of that space. We'd seen a pretty limited number of these phenotypes we could induce, and we had some skepticism. Maybe partial reprogramming is pretty limited. Maybe we're not going to have the degrees of freedom we need to be able to access that axis of cell age. But with each experiment, we found more and more trajectories that you can induce in these old human cells, more phenotypes you could cause them to adopt. And so today, we've actually found that that diversity expands every time we run a new experiment. We keep finding more phenotypes that we can induce upon these cells. And it suggests to us that if we're able to properly define the young cell state we want to induce, if we're able to properly define the young cell functions we want to engender, then partial reprogramming might be a sufficiently expressive set of interventions that we can achieve it. And now, for those of you in the audience who are biologists, you've probably seen now a bunch of nonlinear dimensionality reduction plots, these very reduced representations, and you might be wondering, are these experiments actually generating robust data? Have we done the checks we need to do to make sure these data are reliable? And so I'll show you just a couple quick examples for the ways we check ourselves and ensure that the data we interpret are actually sufficient to teach us something new about biology. So the way we do that is by including some number of controls, some number of TF sets where we have some idea of what they should do. If we see them do what we expect, we can put a green check mark next to it and believe the results we see from those where we have an unknown. As just a few examples, here I'll show you an example where we introduce the Yamanaka factors. We expect these to make an old cell look younger. I'm showing you here the cell age score on an x-axis. That's an ML model my colleague Greg will tell you about soon. And you'll see these Yamanaka factors make these old cells look a bit younger. So check on that axis. Now, this is still a pretty complicated measurement. There's a long story about how we get to cell age. So we also love to do really simple experiments too. Really simple things like cell growth. It's hard to mess up this measurement. We know what some of these TFs should do, and we found that we can indeed reproduce this with our system. So hopefully our bona fides are established. We can go on and actually interrogate some new biology and hopefully get a bit more exciting. So when we started the company, we had a few really unanswered hypotheses that have kept me up at night over the past couple of years, and I'm happy to say I now get some better sleep. One of those hypotheses that Brian alluded to is that we'll be able to find these TF sets that reprogram an old cell to be more like a young one without changing its cell type. And honestly, it's pretty audacious because other than the Yamanaka factors, there aren't many TFs that are known to change cell age at all, let alone while doing so without changing cell identity. And so we're not sure how many TFs there are that might do this or whether it's really an expressive family. We've also hypothesized early on that this combinatorial space means that there are actually many possibilities, many ways we might achieve that goal. But maybe just individual TFs actually explains most of the variation. It's a much smaller set of options than we thought we had when we started. And finally, we've always hypothesized that we might be able to turn these TFs on briefly, like we do in our experiments, and get durable changes in cell function in a way that might be therapeutically useful for a patient. So you get a medicine briefly, but then you have a long-term response that benefits you over time. When we started the company, there wasn't a ton of evidence for that. And so it was an ambition and a hope, but not something we could back up with data. And today I'm happy to share with you some of the evidence that's helped me get better sleep over the past 6 months or so. So first, when we ran some of our larger screens, we were really excited to go in and ask, do any of these TFs seem to change cell age in a meaningful way? And time and again, we see the Yamanaka factors do it. Those are the controls I told you about. Great, we can check that box. But we've also found a number of other novel TFs that seem to do the same thing, and often to a similar magnitude to the Yamanaka factors. So when I first saw these results, I'm what you might technically say was really stoked. And then I got less excited when I realized there's a way this could be less exciting. maybe these are just Yamanaka factor lookalikes. Like maybe we've fit the letter of the law here, but not the spirit. We haven't really found anything new. And so one of the experiments we ran to try and determine whether or not that was the case was we looked at where these TFs sat within the family tree of other transcription factors. And so what we're showing you here on the right is an embedding of all the transcription factors that are known based on many of their protein features. The Yamanaka factors are blue, the new TFs we found are pink. If we found a bunch of lookalikes and we hadn't really found much new at all, you'd expect all the pink dots on top of the blue dots. But instead what we see is that they're distributed relatively evenly throughout that space. Many different TFs and many different families of TFs seem to be able to change cell age. Suggests there might be many solutions to this general problem and many different ways we can tackle that cell age reprogramming challenge we took on. Hopefully, that diversity means that some of them are able to reprogram cell age without changing cell identity. Now, we also hypothesized that combinations would be important. Part of the reason we're excited about partial reprogramming is there's a lot of different ways we might solve this problem if you think the combinations have unique effects. Now, when we started, we didn't have data for that, but we took on a really hard challenge anyway. We decided to take on the challenge of trying to deliver multiple TFs to individual cells so we could run these combinatorial screens. We presented this idea about a year ago, but at the time we could hardly get one TF into cells. Turns out this is really hard when the cells are from real people and not a cell line. And so after many hours locked in a conference room we called the war room, being very frustrated, we were able to increase that number considerably so we can deliver almost arbitrary numbers today. And we've run screens with many TFs and many combinations at once. And we've been happy to find that that wasn't just a waste of time. Actually, most of the combinations that seem to change cell age do come from multiple TFs together, not just one at a time. So when we double click in there and ask, why do these combinations seem to have an effect that's greater than singletons? Some of that's just additive. 1 + 1 = 2, 2 is bigger than 1. That makes sense. But sometimes we also find something a bit more interesting, some nonlinearity, some synergy in technical parlance, where you have two TFs that might push cells in different directions. One pushes left metaphorically, one pushes right. When you add them together, you get something like up, a totally unique state you wouldn't have expected from either of those TFs alone. We can see that in some embeddings here that represent the cell's state in a 2D grid. You can also find this in cell age scores, where two TFs that might not change age at all on their own actually do so when you add them together. And again, just to gut check ourselves, make sure we're not fooling ourselves with a lot of complexity. You can even see this in really simple phenotypes like cell growth, where two TFs that don't do much individually actually have really big effects when you put them together. So those two results, that combinations have big effects on cell age and that we find synergy, suggest that that rich space of combinations actually does mean we have a lot of options for how we might change cell age, not change cell type. Now, finally, we've been really excited to find TFs that might be able to translate into medicines, where we turn them on briefly and then get a durable effect. So I can take an old cell, push it toward a young one, and have it stay where we put it. Now, we didn't really have a lot of evidence for this when we started. It was just a hope. And so we've been excited as we've tested these thousands of combinations that we can now ask this question in a more rigorous way. So what I'm showing you is the effect on cell age of many different TF sets on the x-axis when we have those TFs turned on, and on the y-axis after we've had them turned off for a number of days. And what you see there in the bottom left corner is that a number of these TF sets are able to reprogram cell age in a way that is durable. We pushed it, the cell stayed where we wanted it to be, which is closer to its younger self. Now, you might wonder whether this is unique to this particular way we define cell age with our machine learning model. And so just to build some confidence, we've also looked at this with more traditional ways of examining gene expression programs. Here I'm showing you one gene expression program that is related to how T cells respond to immunotherapy. It's MNIS signature. Signifies how long they can persist when they're attacking a challenger. It goes down a lot when you get older, so unfortunately our T cells do worse when we're old, but we can restore it with partial reprogramming, and it turns out that's actually durable. It goes up not only when we have the TFs there, but even after they've been removed for a while, suggesting these medicines we've imagined, while not necessarily near term, are possible. So with that, I'll just walk you through a roundup of what we've just learned. Yes, there are some TFs that change cell age other than the Yamanaka factors, suggesting that our overall hypothesis that if we go out hunting, there's gold to find, is correct. And finally, that those combinations do indeed seem to have larger effects than singletons. We didn't waste our time building that machinery, but it actually unlocked this large space of possibilities that we can now go search through. And that some of those effects we're finding do seem to be durable, and then they therefore allow us to translate those results into medicines later. With that, I'd be remiss if I didn't mention that all of that biology I just showed you really required a lot of novel technology development as well. So I'm excited to welcome my colleague Burak Dura on, who helped develop that along with his team.
My name is Burak. I lead our single cell technology team at NewLimit, and happy to tell you about the single cell tools that we are developing. Brian gave you an update in terms of the progress we made since the last update. On the cellular genomics front, we have 5x the number of cells we profiled, and we did so from many more donors. And we have also cut down the cost significantly per reprogramming test, roughly 75% reduction. And as Brian mentioned, that gives us more shots on goal in terms of identifying new factors that can be medicine candidates. And in the next few slides, I will be talking about some of the single-cell technologies that we have been using to achieve these numbers. Now, single-cell screening is pretty common. A lot of research groups, a lot of companies are doing it. But combinatorial screening is still pretty difficult. As Jacob mentioned, we are interested in identifying the combinations because they have larger impact on the cell age. So if you look at this plot, though, as you try to add more factors to the cells, recovery becomes exponentially more difficult. So this is the main problem we had to address in our single-cell technologies, such that we can achieve meaningful combinatorial screening. Now, in our group, we have basically took on the single-cell technologies out there, and then we optimized them very carefully such that we can more accurately detect the TF combinations. This basically meant that we improved on the library preparation protocols by including several molecular improvements on the workflow, and particularly targeting the signal-to-noise ratio in these assays. And the signal-to-noise ratio here refers to number of real molecules we are detecting from these cells, basically. And obviously, the more molecules you are recovering from a cell, the more accurately you will be able to call and demux the perturbations that we are delivering to them. And happy to report that we were able to increase that number by 4-fold. And by doing so, we can now more accurately detect these TF combinations in cells compared to other baseline methods. And when we take this approach and apply them in our screens, we are able to detect many more hits compared to what we would have detected using more suboptimal protocols, for example. Hopefully, this gives you an idea how we are using single-cell technology improvements to help us do combinatorial screening more efficiently. And other than performance, we also care about the cost and cycle time of our screens, because that will enable us to do more TF combinatorial screening, which will give us more chance to discover new factors. On that front, we have reduced the single-cell sequencing cost significantly, both on the reagents front, also sequencing front. That took many miniaturizations, many optimizations, even choosing cheaper reagents over more expensive ones and haggling with the vendors, actually. And that basically translates into much lower cost per set that we spend, which gives us more shots on goal. And basically, we also improved our processes and operations to cut down the cycle time in our screens. And basically, with this lower costs as well as reduced cycle times, we now, for a given budget and given time, do more screens, profile more cells, and hopefully we will be able to identify many more combinations. And we don't want to stop here too. We want to increase the scale of our screens even further. And for that purpose, we have been actually developing custom assays, custom single-cell genomics assays. So far, we have been using the single-cell technologies to both demux the perturbations, but also record their cellular phenotypes, such as gene expression patterns. But going forward, we also want to start doing selection-based screening, and John will tell you more about those functional assays that we are developing. And basically, when we are developing these custom assays, we are going after the perturbation identities and not cellular phenotypes, and that allows us to cut down costs even further. And we're happy to report that we actually developed the assay that can very efficiently detect these TF combinations, but do so at a relatively cheaper cost, actually 100 times cheaper than what we pay for a gold standard method, for example. And for a given budget, that means that going forward with selection-based screening, we can improve the TF sets by 100-fold in our future screens. Now, hopefully this gives you a flavor in terms of how we are using the single-cell technologies to do better and more efficient combinatorial screening. And now I will hand it over to Greg, my colleague, who will tell you how we are using the single-cell data sets in our machine learning efforts.
I'm Greg Johnson. I'm one of the co-founders. I work with the team that provides a lot of the computational analysis that you've seen. And we also build some cool machine learning models that I'm going to talk about. So now that we can run these large screens and we can read out which cells have received which perturbations, we've been able to scale our platform. And we've more than 10 times the amount of data that we've acquired previously. And these data unlock two technologies. They allow us to measure the age of cells, and they allow us to predict the age of cells once they receive perturbations. What we're doing in conjunction with the lab are stringing these technologies together to reduce overall screening time and cost. We hope that our predictive models allow us to identify hits, be able to pass those forward for downstream analysis, and also design new experiments that find more hits. And this becomes a virtuous cycle where the faster we go, the bigger we go, the better we get. But before we get there, how do we measure the age of a cell? We take cells from young and aged donors, measure their mRNA profiles, and then use those data in machine learning classifiers to disambiguate these two populations. Over the course of the last year, due to the high quality data that Burak and his team is generating, and some methodological improvements, we've been able to dramatically improve our model performance. Our models generalize well to new tasks, and as a result, we've set some ambitious goals for the remainder of this quarter. And our models perform well across diverse cell types, building confidence that we can use these for different indication areas. Now that we know our models are performant, how do we identify transcription factor sets that recover the phenotypes that we're interested in? Well, we take cells from aged donors, introduce transcription factor sets to those. Using the same models that I mentioned previously, we measure the cell's mRNA profiles, and we use the output of these models as a score, a phenotypic score, to say whether or not the cell looks older, or hopefully, whether or not the cell looks younger. What I'm showing you here is a diagram of all of the transcription factor sets that we've profiled. I hope you can appreciate that there's clusters here that are similar phenotypes. So the mRNA profiles, the molecular profiles of the cells are very similar under particular transcription factor set combinations. And then what we can do is we can score each one of those transcription factor combinations. So in this figure, purple these factor combinations make the cells look older, green makes the cells look younger, and we can draw a threshold and say, okay, this is a strong enough signal, we think this is a hit. And what I'm showing you here is a diagram of all of the hits that we've gotten over the last year. I hope you can appreciate that the screens are getting more hits and we're running screens faster and faster. What do we do with these hits? Well, we send them to our immunology team that we're going to talk about later for downstream functional analysis. But there's still a really big problem. As Brian mentioned earlier, there's far more transcription factor sets that exist than we could possibly measure. What we're building is in silico reprogramming models to take representations of cells, representations of transcription factors, and directly predict gene expression or the age scores that would result from those perturbations. Our models perform quite well. It turns out that although this is a hard problem, we've been making significant progress. We beat several baselines, but more importantly, we can use these models to design new screens. We can build screens that are much smaller, give us far more hits, and we hope to use this to accelerate our discovery process over the next year and subsequent years. Now I'm going to hand the mic over to John, who's going to be talking about what do we do when we find these hits.
My name is John Leonard. I'm the Director of Immunology here at NewLimit, and I have the pleasure of telling you about progress we've made toward our 2 therapeutic programs that aim to restore youthful function in the immune system and the liver. Over the course of the last year, we've added 1 new therapeutic program, which I'll tell you about in a few minutes. And importantly, we've built several assays to measure critical cell functions that are important for tracking how far we've made it along the path toward our goal. So as we've just heard, we have both experimental techniques and computational models that allow us to identify transcription factor sets that seem to make cells look phenotypically younger. And that's very important, but at the end of the day, what we want to do is really rejuvenate cell function. What's interesting is that from these same experiments, we can get hints that we are actually modulating functions that matter. For example, we can identify factors that seem to modulate proliferation or cell growth, factors that increase or decrease expression of critical effector molecules like cytokines, and even factors that nudge T-cell differentiation in one direction or another. So these all point us in the right direction. They help us identify factors that look promising, and ultimately then we need to test whether they do indeed restore cell function in more traditional in vitro functional assays. Over the course of the last year, across our 2 therapeutic programs, we've added a total of 7 assays to measure critical cell functions. In the context of our T-cell program, this includes key functions like cytokine production, the ability to kill target cells, or the ability to help B cells produce antibodies. And I show these graphs not to get you bogged down in lots of detailed data, but to emphasize the point that whereas a year ago what we had to show you was cartoons, now we have gathered data measuring cell function across all of these important parameters. And that's a testament to the hard work of the team. So why are we doing this? Well, our ultimate goal, we think that we can use these assays as a sort of ruler against which we can measure to what extent functionality is lost over the course of aging, and how well we're able to recuperate that function through partial reprogramming. So which functions matter? What happens to T cells as we age? It's a basic question, and one that lots of smart people have been working on for many years. As it turns out, we understand very well in the body, in vivo, that the immune system declines, that the T cells can't do their jobs quite as well. But it turns out measuring this process outside the body in vitro has been very technically challenging. So the team has focused a lot of the past year on trying to identify in vitro assays with which we can robustly detect functional differences between cells from younger donors and aged donors. This involves building out a biobank of blood cells from donors of various ages and testing them across a wide range of functional parameters. Suffice it to say, the number of parameters we could possibly want to test is very large, and so we have to be very incisive about where we choose to search. And so this structured search is informed in part by work of others that have come before us, and in part by our knowledge of the underlying biology of disease. All of this work is with the ultimate goal of being able to stand up assays that allow us to tell an old functioning T cell from a young functioning T cell. Now, this is very much still a work in progress. This is an ongoing endeavor of the team, but I'm excited to share some data from one of these assays that we've developed to this goal. In this assay, we isolate blood cells from younger or older donors. We culture them in vitro for a period of time, and then we're able to assess how they fall out across a variety of functional states. What we observe is that cells from aged donors adopt a different distribution of these states than do cells from young donors. And what's really remarkable is that this information alone is sufficient to allow us to tell you with relatively high certainty whether a tube of T cells came from a younger donor or an older donor. And so I think we will be the first to tell you that to acknowledge that we don't think that these types of in vitro experiments are necessarily a high fidelity model replicating what's happening in the body. I think that this is just well understood that there are limitations to this type of science. However, we do think that by building out a suite of these types of age discriminating assays, that will enable us to take the large number of hits that Greg and Burak and their teams are generating from these phenotypic screens and really winnow down to which combinations of transcription factors we think are likely to move the needle on critical functions, in essence serving as a filter to help us decide what factors we want to test in more biologically or disease-relevant preclinical models. And so, of course, why are we here? We're here because we want to try and solve some of the underlying causes of human disease. I think as everyone has become aware over the last few years, viral infections are a leading cause of death in the elderly. And so we thought that this was an apt place to start to begin to develop in vivo models for immune resilience in which to test these transcription factors. In one such model, we can take aged mice and young mice, infect them with a respiratory virus, and measure things like survival, and as well as the immune response. And we, just like others before us, observe that younger mice survive with have better survival in the case of viral infection, and they produce a stronger, more robust immune response. And so we think we want to use these types of preclinical models to test whether some of the factors that make cells look and function more like young cells in a dish might really have an impact in a biological and disease context that we care about. Okay, so we've talked a lot about T cells today as the first program that NewLimit was founded upon. But earlier this year, we launched our second therapeutic program, which is focused on hepatocytes of the liver. The liver performs a number of important functions in the body, and it has this tremendous potential for regeneration in response to injury. But this regenerative capacity is diminished as we age or in response to certain injuries over time. And so we think that this really represents a tremendous opportunity to meet a large unmet medical need, both in the context of acute liver injury, as well as in the context of more chronic conditions such as metabolic syndrome. We envision a scenario where you can transiently deliver reprogramming factors to the liver, and that this will induce a more youthful phenotype in those liver cells and allow them to regain the ability to regenerate after injury. Now, as I alluded to, this program really only got started a few months ago, but I'm happy to report we've already started detecting functional differences between hepatocytes from older and younger individuals. So one of the key functions the liver performs in your body is processing foreign compounds, processing foreign substances that come in the body. And if we measure the activity of some of the enzymes that perform this process, we can indeed see differences in enzymatic activity between cells from older and younger donors. And just like with our T cells, this information alone gives us a reasonable ability to classify whether cells came from a younger liver or an aged liver. So again, this is early days for the program, but I'm confident that a year from now, one of my colleagues will stand up here telling you about the exciting progress that they're making. Great. So today, we've shown you how over the past year, we've developed both experimental and computational approaches to help us identify transcription factor sets that make cells look younger at the phenotypic level. And we've also started to build up functional assays that will really allow us to test whether we've improved cell function. To date, we've been building out these functions more or less in isolation, but over the next year, we really hope to align them and string them together to form the basis of our therapeutic discovery pipeline.
Hi, I'm Blake Byers. I'm one of the co-founders here at NewLimit. And I can tell you a little bit about the handoff as we go from discovering this passphrase to youth, this set of transcription factors capable of reprogramming old cells into young cells. The thing is, that's not the end of the NewLimit journey. We were not set up to just do basic research and discovery. We're here to make products that actually make people live longer. And so what do we do after those initial discoveries? Well, we move into various therapeutic areas. So the T cells can be, if you come up with a set of transcription factors capable of reversing the age of T cells, there's a number of immunology-related diseases that you could go into and treat in human patients. These might be diseases of the immune system or an ability to ward off infectious disease insults. In our hepatocyte program, there's diseases of the liver, of metabolism that we could go after, including NASH or ASH, where we think that reversing the functional age of someone's endogenous hepatocytes could treat or cure their disease. Over the next year, we'll also be launching our third cell type. And in the coming years, we'll be launching additional cell types every year and at increasing frequency. And the point of all this is a whole suite of products that we hope to develop over the coming 10, 20 years, where the collection of them could significantly extend human health span 10 years or 20 years. And there's always some chance that on this journey, we find a set of factors, some common pathways, where we've realized there's like one set of factors that works across many cell types. But we don't want to bet on that. We want to build a system that is almost like cell type agnostic as we churn out these phenotypic discoveries, moving into functionally validated hits, and then to clinical disease programs. Unfortunately, the whole initial part of the process that you heard about is really just discovery. At this point, the team would be surprised if it's not possible. It seems like with all the work that we've been doing, age is very likely to be plastic. It's very likely to be manipulatable with the tools and techniques that we have. We don't know if NewLimit's going to do it. We still have that burden ahead of us to prove that to ourselves and to the world. But after that, we have to turn it into a medicine. And we actually fully expect that turning those initial discoveries into medicines will actually be harder than making the initial discoveries themselves. So this is still work a few years out, but gives you a taste of some of the kinds of experiments and kind of development that we'll have to do to turn discoveries into medicines for people. I'm going to give you a flavor of what a clinical study could look like. I think some common detractors we hear about working in aging at all is that it will take an impossibly long time, decades, to demonstrate whether or not your therapeutic actually had an effect on people's lifespan and health span. We take a different view here, which is if you can reprogram the age of a specific cell type, if you can take an old T cell, turn it into a young T cell, or an old hepatocyte, an old liver cell, and turn it into a young liver cell, that you can go after very specific diseases, very specific indications that are well trodden, where other drugs have been developed for those indications already. And in some cases, your readouts of your pivotal study might even just be 6 months for a patient, because the burden of these diseases is so high that you can see differential outcomes much more rapidly than requiring decades. And so if we string these kinds of clinical developments together across multiple cell programs, then we could start to see an accumulation of that really affecting patient lifetimes. Finally, I want to close on the underlying substrate that enabled all of the work that you've seen, which is actually like building a company. This is really all the work is a result of people and the systems that we've built. And I want to drive home maybe like the most important point of the founding of NewLimit, which is like we're making products to make everyone healthier. Now that might sound trite. It's like, of course you want to make products that make everyone healthier, but this is actually very uncommon in biotech. Most biotech companies are building products for very small numbers of people. And don't get me wrong, we should do that. There are patients that need bespoke gene therapies. There are patients that are suffering from certain forms of cancer that might only affect 1,000 people a year. We should develop those drugs. But we should also develop drugs that work for everybody. If you look at GLP-1s, also known as Ozempic, Wegovy, they've added $300 billion of enterprise value to Eli and Novo over the last few years. That's worth more than every biotech company founded for the last 30 years combined. So it gives you an example of sometimes you want a few asymmetric bets. You want a few things that are real outliers where, yes, it's riskier, but in the success case, it has a bigger impact than everything else you're doing combined. So I'm not making an argument of we should shut down all the drug programs. I'm saying right now we're spending roughly 0% per year on aging, and it's maybe the most important thing we should be working on, and so we should do a little bit more of it. Now, like working at aging also probably sounds a little scary. There's not been a lot of progress in aging. People have been trying to develop aging drugs for thousands of years. There's been people selling you snake oil for that long. It has a little bit of a negative brand because of the lack of progress. But we shouldn't look backwards to determine how much progress is possible. We should look forwards. And insurmountable as it might seem, I'm here to tell you that it's not, because a small team working for the last year and a half has actually made this much impact towards these goals. We've had 25x improvement in reprogramming sets tested. We found new phenotypic age hits. We are increasing the efficiency both in terms of cost and time and turnaround, and all of that with just 15 additional people. So like small teams can make real impacts here. And this is my call to arms, is like we need more good people. You heard from my colleague earlier, we have a super high bar for talent. We're averaging 100 interviews for every offer we give out. But that's not because we don't need people. We need more great people. And I'm sure there's many talented people out there that we just don't know about. So I really encourage you to apply to NewLimit. Here's our careers page. We have a bunch of open roles, but also if you just think you'd be really good at working at NewLimit, we're always flexible in figuring out where good people should plug into the organization. So with that, I want to thank you. Thank you for attending. We're going to open it up to Q&A. So I'm going to invite my colleagues to come on stage in case any of them need to field questions. Come on up. Thank you. All right. I see one in the back. Do we have a mic for him, or I can just repeat the question too?
Just shout it.
Right.
Yeah.
Oh, perfect.
Super cool, super interesting, and I think I really appreciated the transparency into how hard it is to build a platform, having been there. I guess given the ambitious mission of every cell type partial reprogramming, I would think you guys would want to work on delivery, as that's going to be a challenge outside of the liver, and I'm just curious what you think about that.
Yeah, definitely going to be a challenge. We decided where to place our bets early on in the company, and we thought, there's a lot of people working on delivery of various kind of molecules with cell type specificity, appropriate tropism. We're kind of rooting for all of them. At some point, we'll also develop our in-house program, but we're only going to do so when it's worth really an in-house dedicated effort where we can feel like we can make differentiated progress over the rest of the field. So for now, we're talking to all the groups, both the companies and the labs working in this space. We would love someone to just solve it and then we can go shopping for it. But I assume we'll have to do some of our own development at some point. I'd expect to do that in the coming few years. Great question.
Programming. Do you expect that you're going to have to redo searching for the TF sets for every cell type you're interested in?
Yeah.
Short answer, we're betting we do. We're hoping we don't. It seems like most reprogramming factors have an effect that's dependent on, sophisticated speak, the local chromatin context of the cell, less sophisticated speak, whatever that cell's job is at the time that you reprogram it. And so already we've started to see that reprogramming effects we see in primary T cells are different than what other people see in certain types of cell lines, which are different cell identities. And so we imagine there won't be a one-to-one mapping. We are hopeful there might be some general principles you can extract from one cell type program that narrows the search space in a future cell type program.
This is mostly for you too, Jacob. So the Yamanaka factors are finicky in that you have to, if you want the youthful direction without the dedifferentiation, you have to hit the timing right. You didn't talk about this, but is part of the platform and the screening and the funnel sort of identifying the amount of finickiness to the different combinations? And, can you describe a little bit about how that aspect of the platform works?
Absolutely. Thanks for the great question, Carl. So what Carl's referring to is that there are some early results that you can change cell age with the Yamanaka factors, but they do also change cell identity at the same time, as Brian introduced at the outset of our talk. So what people have found is that the safe dose range, where you see reversal of cell age without really changing cell identity in a way that's pretty darn dangerous as in kills mice in 7 days, is less than twofold. So it's really difficult to imagine using those as medicines, which is part of why we've gone on this search for novel reprogramming factors and why we think it's worthwhile. So part of the way we've built all of our technology is that we have control over not only which TFs we deliver, but exactly how long they're turned on. And then just as Greg introduced the idea of scoring cell age using machine learning models, we can also use those to ask the questions of what identity a cell has at a given time. And so you can quantify for every reprogramming factor set, well, how has it changed cell age? How has it changed cell identity? And then once you've got a hint of some sets that are really interesting, you can start to vary that timing parameter as well in a narrower search space. So I think it's a really great, astute question, and we've tried to set ourselves up so we can tune it later on. We're not quite there yet in terms of development, but maybe in a year or so, check back and we'll hopefully have some data for you.
So I have two questions. The first one is kind of ontological, right? So if you want to, how do you know that the effects of your drugs or your TF combinations are actually acting through the pathway of making them younger and therefore more functional, as opposed to reversing some cellular mechanism that makes them better in your functional assay? So more specifically, I'll give an example. Like if you put a mouse through chronic viral stim, and now the T cells are exhausted, right? How do you know that you're not just finding transcription factors that reverse that exhaustion and make them better at, fighting against that viral infection, which, just to be clear, would be great, but may not necessarily be happening by making them super young T cells?
That's an excellent question. It's one we grapple with on a daily or weekly basis. I think the immunology team knows what I'm talking about. So I think about this a couple of ways. One is, of course, in a single assay, you might find things that move functionality around on that one axis. Again, might be great, maybe not precisely what we're going for. Our thinking is that if we can measure enough different functional parameters, the odds that something will, by random happenstance, be able to modulate functionality across all these different axes in the direction that we expect seems somewhat low, right? So if you imagine the chance of resisting exhaustion, in addition to changing a certain differentiation phenotype of the cell, in addition to changing the cytokine profile in some degree, we think that by building this kind of layered approach to measuring different cell functionalities, that might enable us to kind of to catch these things more efficiently. The other aspect of this is obviously the whole single cell profiling approach. We have, in some sense, the phenotypic age score to go on as well. And so if we see factors that might be modulating an inflammatory response or a response to exhaustion, but don't seem to be moving the needle on the other metrics that we have to quantify cell age, that's also some indication for us.
So my second question, if that's okay, is really how to kind of query how you guys think about time, right? So the Yamanaka factors are interesting because you can put all four in at the same time, right? But then, if you start to screen things, at T1 and then at T2, obviously your statistical combinations explode, right? And how do you guys think about approaching that, since it's very possible that there's an entire hit space that can't be accessed by just stuffing them all in the same bag at once?
You're totally right that there may be some sequences of TFs where when you reprogram them in a particular order, maybe you need A, then B, then C. You can't deliver them all at the same time. You'll get an effect that's positive and really exciting that you couldn't access otherwise. I think we've tried to constrain our search space using some of the limitations that we're going to encounter downstream when we make therapies. And so one of those limitations is that it would be much, much easier from a therapeutic perspective to have a medicine you could deliver all at once with one formulation than something where you had to have a very carefully orchestrated series of events that play out into patient cells. And so in a way, the hit space of things that work when you deliver them all at once with, maybe some controllable stoichiometry, but otherwise similar timing, is way more exciting in terms of how easy it is to turn into a medicine than the hit space of something with careful sequencing. So that's where we've started to look. Now, if we weren't finding any hits there, I think we'd very quickly start to explore some of those spaces you're describing. And I think that's an area we hope to get into soon. But that's why we've prioritized this regime.
Cool. Congratulations to the whole team to the progress.
Sorry, who are you?
Okay, Brad, and then we'll go back.
Okay, so yeah, congrats on all the progress, guys. Great work. I appreciate that most of the work to date has just been in creating a discovery engine, and that makes a lot of sense at this stage. To be that guy that asks the direct and maybe really coarse question, how much have you actually reversed cell aging at this point, or is it just too early to even ask that question?
No, that's a great question. So, we have these phenotypic age hits. It's more like an indication that the platform is working. I wouldn't say any one of those we have high confidence. Once it goes through the battery of functional assays, like we are sure this is it. Two big places where we need to improve before we can have that confidence is this functional assays that John was talking about. The other is continue to improve our cell identity models that we get from our transcriptional data that we didn't even really talk about in depth here. Those two things are very fresh work. In fact, we had data hot off the press this morning. We're like, man, it's too late to include it. And so I see the results so far as more like we're on the right track rather than here's the final answer. And hopefully in a year or maybe less or maybe more, we'll be able to come back and say okay, this is something we're willing to progress and we feel like has a shot at being a real medicine.
Thank you very much. This is excellent progress. It's very, very interesting what you're doing, guys. I guess I have a more forward thinking question. Is imagine you solved it on the discovery side, right? And you want to develop an actual therapeutic, and then all of these regulatory questions will come in, right? Like what's happening with immunotoxicity, dosage, how many times you need to. How many doses you need to administer and all those kind of things. So I guess my question would be, are you seeing yourself as a company who essentially consults the large pharma companies later that will want to deliver those, like that they will take on those challenges, and you come up with the solution for them, like with the correct set of transcription factors that you provide to them, and they take on all of those challenges? Or do you also want to address those challenges yourself?
I think it's much more likely that we're going to want to address them ourselves. I think outsourcing like a key component of the drug development process to someone else is something we're very unlikely to do. Now, that said, there might be other technologies that are really valuable to bring in. We had the question earlier about LNPs with tropisms to cell types we care about, or even engineering the mRNA in those LNPs themselves. We would love to go and work with groups that had already solved those problems, but putting them all together, we think it's unlikely any other group would care as much as us about getting to the right answer. Now, that said, even just the indications you could treat with a T-cell product is more than NewLimit could ever fund clinical studies for by ourselves. And we have a hepatocyte program. And we're going to have a third cell type, and within a few years, a fourth, a fifth, and a sixth. Each one of them would have many more applications than NewLimit could do on our own. So there might be at a point, and sometime in our future, where we'd want to partner to kind of help fund the development of those, but we would likely want to do most of the work ourselves in-house.
Do we want to take a virtual audience question?
No, because we got one more, and then we can.
Okay.
Thank you, everyone, for their great presentation. Quick question. What kind of role do these transcription factors have in the initiation and the maintenance of senescence? And is the combination of multiple transcription factors, does that lead to a reduction in senescent cells?
Shorthand in terms of induction and senescence, I think that's actually still an open scientific question. Not my direct area of expertise, but it's a pretty complicated process. In terms of can you reverse senescence using reprogramming factors, that was actually one of the first exciting results that got people interested in this area of using reprogramming factors to reverse cell age. So we know, at least in the limit case, you can take a senescent cell, you can make an ESC from it, or ESC, an embryonic stem cell, an iPSC more formally. You can redifferentiate that back to the skin cell it was before, and it looks just like a young one, as if it had never been senescent. There are beautiful papers we can share later. But so we know that's possible in the limit case. We don't know if something like a transient partial reprogramming intervention today, where we could deliver it as a burst of mRNAs, maybe something you could take as a medicine in vivo rather than doing this ex vivo in a dish, could work that way. But at least the existence proof is there.
All right, Peter, and then we'll do the online question.
So you have a mysterious third cell type on the far right. You probably won't disclose to us, but maybe you could say a word about your top 3 or 4 candidates, and how do you think about what cell types to go after in what order?
Yeah, I'll start with the process. So I think the academic way of doing cell types is you do the one that's in the lab. We try to select on a few different axioms, and we almost start with a patient. So we say, all right, what cell types, where if we reverse the age of that cell type in a person, we would treat some specific disease, and what's the clinical and commercial development potential of that disease? What would a clinical study look like? Is it reasonable to fund it? Do you have reasonable endpoints that are measurable? Okay, that kind of narrows things down a little bit. Okay, which of these cell types can we actually do the discovery work in human cells? All the T cells we're screening, all the hepatocytes that we're screening, all that data is from people, from old people and young people. So that also limits certain cell types that we can get access to, or the volume of those cell types that we get access to. We also want there to exist some idea of functional assays. You heard that, that's kind of the final boss of our discovery process. So if we have to completely de novo invent all the functional assays for that cell type, that's another kind of knock against it. So those are kind of that's kind of the rubric we use. We actually haven't selected the third cell type. I wasn't just leading you on. Yeah, let's hear it. Yeah, I also have glial cells really high on my list, but that's But maybe it's possible. Yeah, thank you for the question, Peter. And then let's do one online one.
Great. This is a question from our virtual audience. How would reprogramming a specific cell type or set of cell types affect the aging state of a person in general?
Well, I mean, the real answer is we don't know yet. We're starting with individual cell types and trying to treat specific indications. But I think, as Blake alluded to earlier, if you stack enough of these up, you could start to have an impact on someone's overall health span and lifespan. We're hoping, but we're not counting on the idea that there could be some common factors between the different cell types, right? And so as we get better at cracking that first password, maybe we've got a couple of characters in the next one and the next one. And our data set certainly is growing. And as Greg talked about, we're seeing some benefits that it generalizes well across cell types. So I think this is one of those cases where we're going to it's a data moat. We're going to build up this data set, and hopefully it'll help us get the next cell type, the next cell type. You could imagine a therapy being potentially developed in the future that sort of, you took this therapy and it addressed a handful of different cells throughout your body, or maybe there's a variety of medicines that ultimately come to market.
You want to do one more? Okay. How long does partial reprogramming of cell age last? You said it lasts at least a few days after the TFs are turned off, but how long?
Excellent question, if you know the answer. So we can only tell you as long as we've looked, which is some number of days, less than a month, more than a couple, that we've looked. And so this is really another axis that, as was highlighted in another question, we are hoping to explore as we narrow the search space. We have some hits we're interested in. We can start to ask this question in a rigorous way. How much dose do we need? And how long does that phenotype last over time? So we look forward to finding out an answer and delivering it to you, hopefully sooner than next year.
All right, on that, okay, we'll do one more.
I was wondering how many more experiments you need to do on transcription factors for a single type of cell for your machine learning model to be accurate to predict what would be the result.
Same answer Jacob had. If you knew the answer, please tell us. I can say that depending on the model and the context, our models are getting better and better. We hope that it is a very, very small fraction. I personally believe it is probably less than 1% of the whole combinatorial search space. But we're going to find out.
All right, that's a great one to end on. Thank everyone for coming. If you know anyone that you think should work at NewLimit, you can tell us or tell them to apply to us. But thank you again. Look forward to seeing you again soon with more updates.